So RSA is not the only method for public key. Other methods are now coming into standards. So those are the methods we will talk about in this chapter. So we will start with Diffie-Hellman Key Exchange, then ElGamal Cryptosystem, then Elliptic curve cryptography. All right? And then end with pseudorandom generation using asymmetric cipher. Okay. So Diffie-Hellman, they were the fathers of this whole public key stuff. And first thing they did actually was, and this is one of the original papers they did, was not so much about encryption, but about key exchange. And again, somebody had asked initially, how do we exchange the key? So Diffie-Hellman had the same problem. How do we exchange the keys? And they had to do it in public. So can we do something right here in public? I can say something to you and you can say something to me. Everybody else is listening. But we can still get the keys across without anybody else finding it out. And here is the method, magic method. Diffie-Hellman. So what they said was that all you need to do is A selects, so there are A and B who are trying to generate secret key. A selects a random number XA and actually selects a prime number Q whose primitive root is alpha. Yeah, generate the whole set. That means the power would be exactly equal to Q minus 1. So you need an alpha which says that the power is exactly equal to Q minus 1, and that is the only time it will become 1, right? So you get alpha, Q, and XA. So everybody understands three numbers you need. A prime number Q, a primitive root alpha, and you need any random number X. Then A calculates Y equal to alpha raised to XA mod Q. So it raises alpha to power A and then does mod Q, and whatever number comes out YA. It sends out that in public into everybody to know that I'm sending it to B, alpha, Q, and YA. B selects another random number XB, and whatever it gets for YA, it raises that to that power by B and sends it, B selects another number XB and raises alpha to by XB, does mod Q and sends by B in public to A. So everybody can see these four numbers in the middle, but what A does is it multiplies, it just raises by B to power XA, because everybody doesn't know XA, so they cannot do this calculation. But A knows it, so it raises power XA and it gets the number YAB. And B does the same thing. It takes the number YA, raises it to the power XB. Nobody else knows XB, so they cannot do it, but B can do it, and so YAB. Now both of them know YAB, but nobody else does. So YAB is the secret key. YAB is nothing but, this is alpha. Alpha raised to XA XB mod Q, because basically YAB is YA raised to XB, right? And YA is alpha raised to XA. So when you raise it to XB, you are raising alpha to XA XB. Similarly, to do it on this side, YB is nothing but alpha raised to XB. And when you raise it to power XA, you are doing alpha raised to XA XB. So let me just change that to alpha. You can change in your slide as well. Now, one of the problems with this book is that they use different symbols at different places for the same thing. If I were to write a book, I would, throughout the book, I will use N for the modulus, P for the prime number, A for the generator, whatever it is. I mean, so the thing is, at different places, the book uses different. Some places it uses G for the generator. Now here in this case, it uses A for alpha for the generator. So that's why there's a confusion. But, and Q for the prime number, see? And they were using P somewhere before, now they're using Q. And some places they use N. So it's very, but anyway, that is not consistent. But they should use consistent symbol. But anyway, so let's just use the symbol that they have in the book. And if you're using their symbols, basically you generate three numbers yourself, alpha, Q, and actually it turns out alpha and Q you don't generate, because how do you find a large prime and how do you find the alpha, which is the primitive root of, what you do is you go to some book and get the alpha and Q from there. So there is an RFC. There, if you go into that RFC, they have alpha and Q. You just read it from there. So everybody knows alpha and q. It's already public. All of us are going to use the same alpha and q. The only thing we have is if I want to generate a key with you, I generate a random number, you generate a random number, and we do this exchange. At the end, we will have this random number, which is nobody else can calculate. Yeah, there are lots of such things because I was trying to be consistent throughout, and then I gave up, and then I kind of rechanged it back and forth because I thought you guys may get confused. So, but anyway, so I'm just using the symbol there. Just in the next section of the same chapter, they're going to use NA and B for XA, XB. Okay, which is something that I don't like to do, but anyway, we'll do it. So anyway, so XA, XB are the two random numbers. Alpha, Q are publicly known numbers. Okay. The reason this cannot be broken is even though somebody knows YA and alpha and Q, and they know that YA is alpha raised to XA mod Q, they cannot do the log. If they could do the log, then XA is simply the log of YA. So this is how you do key exchange. By the way, this is powerful because this is used at in many places, basically in the standards. You go to the standards and you find out how do you do key exchange. Diffie-Hellman, 1976 technology. All right, we're coming to that. So he's asking somebody in the middle can do something? Yes. So before we do that, let's just do an example. Alpha is equal to 5, Q equal to 19. So A selects 6 randomly. So it doesn't have to be a prime number. It's just a random number, 6. And sends 5 raised to 6 mod 19 equal to 7. So it will send 5, 19, and 7. B selects 7 and does 5 raised to 7 mod 19 is 16. Sends it back to A. A computes 16 raised to its number, which is 6, and gets a 7. B computes 7 raised to its number, and it gets a 7. So both of them have this secret number 7, which other people don't have, even though all the communication was in clear text. Nothing was encrypted. All right, it is preferable that the Q be prime such that even Q minus 1 upon 2 is also a prime. And so such primes are called safe primes. And they are safer than the other primes. So that's just a side note. Now the question is, can somebody in the middle do something? By the way, before I go to the middle, everybody understands how it is done, right? Select a random number, raise the primitive root to that power and send it out. The other person selects a random number, raises the primitive root to that power and sends it back, right? And now both of you can do the power because you know your random number. You can get a common number that other people don't know, right? So that's how this thing works. So, but somebody in the middle can play game. This is called middleman attack. For example, Alice selects some XA and sends out 8389. Dart in the middle catches that 8389 and selects some other number 5876 and sends it to Bob. Now, I haven't said here anything about alpha and Q. Let's just assume that alpha and Q everybody knows. So everybody is going to use the same alpha and Q. So all of these are mod Q and all that. I just skip that detail. So it sends 5876. Bob does the calculation thinking that it is coming from Alice. It selects some number, and then says 9267. So Dart now has a secret that only Dart and Bob know. And then it sends another number, 8389, something like that, and it sends 5876 to that one. So now Dart has a secret number that only Alice and Dart know. Every message that comes encrypted here, Dart can decrypt it, re-encrypt it with this new secret, and send it to Bob. Bob thinks, wow, great, this is all working. But it doesn't know that it is working through an intermediate person who is changing everything back and forth. Right? So this is clearly a well-known problem with DH. So the DH does not do authentications. When you do share a secret, you don't know whether that person is the person that is claiming to be. Yes, both of you have a secret, but that person could be somebody else. So it doesn't do authentication. So when you use this DH, you really have to authenticate before. You have to ask the password or something before, something which is known so that we know that this is the same person. Alright, so we know how DH works and we know how it can be attacked. Alright, ElGamal. Interestingly, book has a footnote which says that ElGamal real name is ELG as a lowercase g, but so we all know that ElGamal Cryptography, the name of the cryptography is a capital G, but the person's name is a little g. So we always say ElGamal Cryptography was invented by ElGamal with a little g. So I checked that out. Even in Wikipedia, when the cryptography comes, it is capital G. When the person's name comes, it is little g. Okay? So somewhere mistake was made. But anyway, so the method is basically very similar to Diffie-Hellman, and I prepared this diagram so that it becomes easier to show because the book had somewhat difficult explanation. So it's very simple actually. It is very similar to DH. You have alpha XA, alpha and Q. You generate YA as before. You send it to the other side. But instead of sending a secret and generating secret, the other side can simply encrypt this stuff and send it to you. So that's the point, is that rather than first generating the secret and then encrypting, once you have alpha, Q, and YA, by the way, this is one more thing I forgot to say in the previous case. YA could be called the public key. Okay, so this is all in public. Everybody knows alpha, Q, and YA. Now with this information, B can encrypt a message and send it. How does it do it? It calculates YA raised to K, where K is a random number it selects itself. So this is very similar to the previous case. There what we did was we selected XB and we raised YA to raise to XB, and then that was our secret. So key is, so this is capital K is some number. Then you calculate C1 is equal to alpha raised to little k mod q, and C2 is equal to capital K M mod q. Unfortunate choice of the symbols, K. But anyway, so little k and capital K. You calculate these two quantities, C1 and C2, and you send it to the other side. Nobody can decrypt this. These are ciphertext, C1, C2, but the other side can decrypt it and get back M, which is the message. M is the message, plain text. So how the other side gets it? Okay. So C1 is alpha raised to K mod Q. So what the A does is, it raises it to power XA. It knows XA, nobody else knows XA. It raises to the power XA, that it gives this capital K, which is the same thing as here, YA raised to K, little k. So you see, notice that this is actually YAB. Previously we have called this, instead of K, we have called it YAB. And so that is what it is, YAB. That was the common secret, capital K. And then, using the capital K, we multiply it to M, and we get this ciphertext here, and here we just have to take inverse of K and multiply to the ciphertext to get the little m, and to get the message. So you have to calculate the inverse. Again, you use the tabular method to get the inverse. And this will keep coming. Everything we do, we need inverse. And to do inverse, you need that tabular method. So it's a simple multiplication mod Q to get the ciphertext. The rest of the world actually doesn't know this common secret, which is equal to XA, XB. So if I were to write the book again, I would not use the letter K, I would use XB just to be consistent, at least in the same chapter. So this ElGamal method is basically using Diffie-Hellman kind of thing, getting a secret K and right away using it to encrypt by multiplication. Any question about these two so far? Diffie-Hellman and ElGamal. So here's an example, again very similar to Diffie-Hellman. We select 5 for the random number, alpha is the generator, Q is the prime number 19. So we raise alpha raised to X, our prime number, our random number that we generated, 10 raised to 5 mod 19 is 3. We send in public 10, 19 and 3 to the other side. Other side generated a random number 6. So it raises YA 3 to 6 mod 19. Get to 7, and then it calculates C1, which is alpha K mod Q, 11, and C2, which is 7 times 17 is our message, it's a 5. So C1 and C2 are sent. On the other side, it's also returning the secret, and then inverts it. This inversion, even though it is written here, is 11, actually requires that tabular method. Find it. Once you have that 11, then you can do 5 times 11 mod 9. If there are no questions about that, then we come into really somewhat little bit mathematical concept, elliptic curve cryptography. So when we started the course last time, this was still in theory, not in practice, but now it is in practice. So there are several standards which have included elliptic curve cryptography, so this is not anymore a theoretical concept. And so that's the advantage of using latest book, is to be able to explain all this. So listen carefully as to how the elliptic curve works. So first of all, why do we need elliptic curve is because with elliptic curve, we don't need so big keys. We can use a smaller number of keys and still get the same amount of security. So this is a new stuff, so not as thoroughly analyzed as other stuff, but it's there. So what is an elliptic curve? It's not an ellipse. Elliptic curve is this curve. It has a formula of y squared is equal to x cubed plus ax plus b, where a and b can be changed. So you can select some value for a, some value for b, and you get one elliptic curve. You select some other value for a and b, you'll get another elliptic. Now, the only thing that they have analyzed and they have said, and I haven't found a reason for it, and I have to think about it a little bit more, is that 4a cubed plus 27b squared could not be equal to 0. If that is 0, then this curve becomes some kind of curve which is not good, which is not useful. Other than that, now to see what really happens, I was going to generate some example where this is true and then tell you, but I haven't done that yet. But anyway, so you can select any a and b as long as they don't have this exception. Then we define an operation. If you have 2 points P and Q, we have to define an operation so somehow we can get a field, or we can get a ring, or we can get something. In elliptic curve cryptography, all you need is an abelian group. Now, we had talked about some time ago, group, abelian group, ring, commutative ring. And you remember you have to check out whether something is a ring or not. So that is the thing you have to remember back. So anyway, so if P and Q are any 2 points, then this thing is an abelian ring. Sorry, abelian, not ring, abelian group, not even ring. So how do you define, the key is how you define P plus Q. If you take point P and point Q, then P plus Q it cannot be simply defined that you take the x coordinates and add them up. No. What you do is you draw a line from P to Q. Wherever it intersects the curve, you take the reflection of that on the other side. By the way, this curve is symmetric on y squared. So everything that is plus y is also minus y. So it is symmetric along y equal to 0. So you take P and Q, draw a line, wherever it intersects, you take the reflection of that, and that is P plus Q. That is defined as P plus Q. Now, if you define P plus Q that way, then plus operation, then this whole set of numbers makes an abelian group with plus operation. And infinity acts as an additive identity. Infinity is somewhere there, x equal to infinity, y equal to infinity. That is additive identity. Now this is the problem. It is an additive identity. Additive identity generally is called 0. So that is the 0. The infinite point is the 0. So when you want to double P, so suppose P and Q, and we draw a line, but if suppose Q equal to P, how do you draw a line? If P and Q are at the same point. Then what you do, you draw a tangent. You draw the tangent at P, and wherever it intersects, you find the deflection, and that gives you 2P. Alright, now you can verify the 5 requirements for abelian group. First requirement is that given any P and Q in E, P plus Q is in E. E is the set of all the points that are in this curve given some value of A and B. Associativity, you can verify that P plus Q plus R is equal to P plus Q plus R. Identity, you can verify that P plus infinity equal to, that identity equal to P. Inverse of it always exists. For every P there is an inverse at A level. And commutative P plus Q is equal to Q plus P. So this is an abelian group. And the main thing is that it's not very trivial to add 2 points. Adding 2 points is law of mathematics, because if you want to add 2 points P and Q, each point has an x coordinate and y coordinate. So let us call it xq and yq for the Q point. xp and yp are the coordinates of P. So the slope of this line D is yq minus yp divided by xq minus xp. By the way, this should be subscript. So basically q sub p, sorry, y sub q, y sub p, x sub q, x sub p. Anyway, the sum is here r, and its value xr is b squared. So there's a lot of work to be done. Let me just fix it. Now, book uses, instead of D, the book uses delta, capital delta. I'm going to use the same thing, although I don't think it is the right symbol, because somehow delta gives me feeling of a difference, which it is not. It's a slope. But anyway, we'll use whatever the book uses. I think I've fixed almost all this stuff. Okay, so to find the slope, then you can calculate xr equal to delta square minus xp minus xq. YR is equal to minus yp times delta times plus delta times xp minus xr. And if you want to do 2p, then you use xr is equal to this formula. Now, all of this can be calculated by normal geometry. So there's nothing new here, except that we have done the calculation for you. So I mean, basically, you don't have to calculate the slope and everything else and find the intersection and find the reflection. But if you do that, you should get these values. So if not in this exam, but in the later exam, we ask you to do elliptic cryptography, then you will have to use all these formulas to get XR and YR. All right. So anyway, before I go into the next one, maybe I wouldn't go any further than that. I go into the next one. What I want to make sure that people, it is clear, is that what is that we are doing here. We are taking 2 points and we are defining the sum operation, and this is plus operation, as this thing. Plus of 2 points is simply line, there is intersect the curve, we take a reflection. Now, this plus operation actually acts more like a multiplication in the RSA kind of case. If you add up lots of numbers, that looks like an exponentiation in the RSA case, later on we'll see. And so while it is easy to add lots of numbers, it is very difficult to do the other way around. If I multiply p by k in this method, which means I add p plus p plus p plus p plus pk times, that's very easy to do. Easy means you use those formulas many, many times. However, it's very difficult to find k given k times p. The inverse is very difficult. So while addition is very easy, the inverse is difficult. And that's why this will become public key stuff.